Here's a solution to practice question 2 from week 3. Now, this question asks us to complete quite a lot of calculations in this spreadsheet. And just down the bottom here, I've added some extracts from the week 3 workshop notes, which we'll refer to from time to time as we're completing this exercise. So part A asks us to calculate the sum of x, the sum of y, and their means. Well, the sum of the x values, we'll just have a formula equals sum, and in brackets highlight the cells that we want to sum. The question says don't use the average function, but we do know that the mean is just equal to the sum of all the x scores divided by the number of x scores. To get the number of x scores, I'm going to just use a function called count, which when I give it as an argument all the data for x, we'll just count how many observations there are. I could have divided by 5, but it's better practice not to hard key numbers, and using this count function means that if I was to add some values here, the mean function should hopefully still work effectively. To do y, I'm just going to highlight those two calculations I just did for x and then drag them across and check that the formulas are doing what I expect them to do, which seems to be the case. And that's part A done. Part B says complete these entries using absolute references where applicable in your formulas. So the textbook's notation has this small xi as being the deviation of an x observation from its mean. So that will be calculated as the x observation minus its mean. Now I'm going to drag this formula down, and it will be within the same column, so I don't need to fix any references for the column, but I will need to put a dollar sign in front of the 9 there so that I'm locking in on this particular row for the mean, even as I drag this formula down. So the deviation of -2, that's 0 minus 2, that sounds right. And let me just check this one to see if it's doing the right thing. It is. Sum and the mean, in fact, I'm just going to copy those all across right now because the formula is not going to change. At the moment it's giving me this error message, but once I have values up here, that should work. In fact, the error message is coming because there are no values up here. But as soon as there is a count, this should work effectively. This one is just the previous value squared, so that's equals, point to that cell, caret means the power of in Excel, and 2 to square it. Note that all these answers are positive. Any negatives are being eliminated in the squaring process. The same thing will work for y. I want to get a little yi, I'll get the observation big yi and take away its mean, and I will fix the row reference. I'm going to immediately square that next to it, and then to finish off, I can see that this number is just going to be this column times the value in this column, so it's that number times that number, and I can now highlight all those cells and drag them down to get our answers. The next question says what do the values in F9, that's that one, H9 and I9 represent. So this is the deviations from the mean squared. That's the sum of them. That's the average deviation from the mean squared. So this cell here is actually the variance of x if we treat the x values as a population. So we're dividing by n here. Similarly, this value here is going to be the variance of the y values if we're treating those y observations as a population. And this number here is the covariance of x and y. The question C also says, well, what would be the sample equivalence of these numbers? The sample equivalence, rather than dividing by n, divide the sum of all the deviations squared by n minus 1. So that will be equal to this sum divided by, I'll use that count function again, minus 1, so that's n minus 1 on the denominator, and I'm getting an answer of 2.5 there. I can actually check that by using the variance function, which is by default the sample variance calculation, and it's coming up with a different answer. Why is that? Oh, silly error. So the variance function doesn't want to know the values of the deviation squared. It actually just wants to know the x values. So it should have been these x values that I was feeding into it. That looks better. I think I should be able to copy these formulas across. Try that again. So there I was just using Control C to copy and then Control V to paste as a keyboard shortcuts. Now let me check that one. That's doing the right thing, but what do you think about this one? Not doing the right thing. These, and that's because this formula didn't come across perfectly, I need to be referring to the variance of the y values. So that's them there, and again we get these two things being equal, which is reassuring. The covariance is equal to, if you consider yourself dealing with a sample, is equal to that number divided by count of those numbers minus 1. And the sample covariance, Excel in 2007 and earlier didn't have a covariance sample calculation, but in my version, which is 2010, you can see that it has this covariance sample function. Now it wants to know the x values and the y values, so I will do that, and we see that the values are lining up again. Okay, D. Estimate B1 and B2. It says do not use the intercept and slope functions to do this. Instead, use the formulas on page 8 of the workshop notes. So here are the formulas down here. For B2, it's going to be the sum of little xi times yi divided by the sum of xi squared. So that will be equal to this number divided by this number, negative 1.3, and then the estimate for B1 is the mean of y take away the estimate for B2 times the mean of y. Oh, that looks a little dodgy. That should be the mean of x at the end there. So the mean of y take away the estimate of B2 times the mean of x. It should be the mean of x, not the mean of y. And we get an answer of 5. Now we can check those values despite the question saying don't check. Let's just do that. So there's a slope function which will estimate B2. It wants to know the known y values, then the known x values. The story checks out. And then the intercept function again wants to know the y values, the x values, and we come up with the same estimate. Part E says show numerically that the fitted line derived in D passes through the point of the means. So this is the fitted line here. It says that an estimated y value is equal to the estimate of B1 plus the estimate of B2 times a given x value, and then plus a residual. So in fact, that residual is not part of the regression line. So what we should expect is that if we take the estimate of B1 plus the estimate of B2 times the mean of x, we should get the mean of y if the point of the means is actually on this sample regression line. So I'm going to evaluate this right hand side of the expression without the residual over here. So it's equal to the estimate of B1 plus the estimate of B2 times the sample mean for x, and we're expecting to see 2.4 pop up here, the mean of y. And we do, as expected, because the point of the mean lies on the sample regression line. So that was E. Part F required you to just interpret some summation notation, do the associated calculations, and then, similar to that question we just did, to show that certain equations held or numerical relationships held. So we need to calculate these two things here. That is asking us to square each x value. Done. That is asking us to multiply each x value by the corresponding observation on y. And then we can copy those formulas down. Just check that we're doing the right thing. Yep. The sums have automatically calculated and the means have automatically calculated, though I don't think we need those here. So what we're asked to do in the first point is show that, in fact I'll just do this down here. I'm dealing with the right hand side, which says the sum of capital XI squared. The sum of capital XI squared was this 30 minus n. Well, n is 5. In this case I'm going to take a shortcut and just type that in, 5 observations, and then times the mean of x squared. There's the mean of x, and we'll square it. Now for us to be able to show what we're asked to here, the result should be equal to the sum of x squared, so we should be getting 10. That's the sum of the little xi squared. Do we get 10? Yes. So that relationship does hold true. And the second numerical relationship we're asked to look at is, again, I'll deal with the right hand side, the sum of big xi times big yi, so that is that value, minus n, which is 5, times the mean of x times the mean of y. We're expecting that the result here is equal to the sum of xi, yi, little xi, yi, so negative 13 is what we're expecting. Negative 13 is what we get. G says use the least squares estimates from part D to compute yi hat, so that's the estimated values of yi. These are essentially predictions of yi. These are the values that will be on the regression line. And down here we can see that those values, ignoring again this residual, are equal to the estimated value of B1 plus the estimated value of B2 times xi. So that is going to be equal to the estimated value of B1 plus the estimated value of B2 times the x value. I want to copy this formula down, so maybe you can just pause this video for a second and think about where the dollar signs need to go in order to do that. what we have to do is we're wanting to copy this formula down, and we want the row reference to those two estimates to stay the same, and we want the reference to xi to just float downwards. So there's the calculations. Let's just check that one and see that it's doing the right thing. So C12 plus C11, yes, times the x value, yes. Okay, so each of these is going to fall, each of these points, sorry, the x value and the y, that corresponding y estimate will fall on the sample regression function line. It says show that for these numerical values, the mean of the estimated y values, which is that, is equal to the actual mean of y, which is that. So we don't need to do any further calculations. Those two things are equal, and that's another numerical property of the least squares regression line. Calculate the values for the shaded cells in M3. So here, I think it actually went down to here, is part I. So what's this? The residual for each observation, which is an estimate of the disturbance term. Down here, you'll see that the residual is calculated as the actual y value minus the estimated y value. So that will be actual y minus estimated y. I'm going to copy quite a few things at once. This is the residual squared, and this is the actual x observation times the residual. None of those formulas require absolute references, so I'll drag them down. These numbers here are in scientific notation, and that -16 is saying that this number is actually 0.15 zeros and then the 44409. So these are very tiny numbers, and if I just reformat them into numbers with, let's say, 2 decimal places, you'll now see that they're essentially 0. And in fact, they should be exactly 0. It's just that representing small numbers with a computer becomes a little inexact, and yeah, that's what's causing those small numbers that we saw. Computer rounding happening underneath the what we see. Okay, J says compute the error variance, and you can see down here is the formula for the error variance. So it's the sum of the residuals squared divided by n minus 2. So the sum of the residuals squared, that is this number, divided by n minus 2. Again, I could do that count thing, but I'm feeling a little impatient. I know that 5 minus 2, I could have even just put in 3 there, but 5 minus 2 just shows a little bit more of a trail if I was to come back to this formula and work out where that 3 came from. And that gets us an estimated error variance of 1.4333. I just want to check. I can check this against an Excel function. I'm going to take its square root, and that gets me the standard error of the estimate, which is discussed a little down here. It's just the square root of that number. And Excel has a function, stex, I'll call it, which wants to know the known y values and the known x values. And with that, it calculates the standard error of the estimate, which is essentially the standard deviation of the error terms, or at least an estimate of that. K says what is the variance of the estimate of B2. So that is actually this one here. And And to calculate that, we need to take the error variance squared, or if we don't know that, its estimate, divided by the sum of little xi squared. Where is little xi squared there? 0.1433. So that's actually the standard error of the B2 estimator. And we could check that by running a regression analysis. I don't know of any function that will allow us to check it without doing that though. So finally, there's a bit of a theory question, and I'm not sure why I decided to put this in, but it's there, so let's quickly address it. Which, if any, of the values you derived in C, which were these ones, J and K, so that's that one and that one, which of those could you see if you had hypothetically done a scatter plot for this? Well, let's very quickly do that. Insert XY chart. So you can see this looks to be a downward sloping line, which is why we have the negative slope coefficient. Let's add a regression line to that. Okay, so there it is there, and you can see that its intercept is 5, as we had calculated earlier. So this is a very small, and I won't bother doing any more tidying up this, but this is a very small data set. But can we see any of these values? Well, that there is essentially, or this one here is the sample equivalent. These are the variance of the X scores. And so it's talking about the distribution. If we dropped each of these values down here, the variance is looking at the dispersion of those X values. Perhaps if we took the square root of this, we can more meaningfully compare it. We've got our rule of saying, look at the range, it's 4 divided by 6 standard deviations. We can get an approximation of the standard deviation. And it's not going to be the best approximation here, but that's what this thing here is getting at. The same thing applies for the variance of y or its standard deviation. So now it's looking at the values that y takes, and their standard deviation is being measured by this. The covariance is difficult to talk about the magnitude, but we can definitely talk about the sign. The sign of this is negative, and it corresponds to the fact that these data points are following a sort of like they seem to be inversely related, X and Y. So the negative sign is something that we can see in this graph. Can we see the variance or the standard error, its square root? Yes, if we, to an extent, if we looked at the residuals, which would be that distance, that distance, that distance, that small distance, and that small distance, this is their standard deviation. And you can see that the variation from the regression line seems smaller than the variation for y itself, so the variation of y from its mean. And that's why we see that the standard error for the estimate is quite a bit lower than the quite a bit lower than the standard deviation of y itself. That's because you could say that the regression function is a better estimator of y than just the mean of y is itself. This is measuring the dispersion about the regression function. This is measuring the dispersion about the the mean of y. And finally, this variance of the estimator of B2, that is very difficult to see on this graph, but we can briefly talk about it. Imagine that this was actually a sample and that we took another sample. That would give us most likely another sample regression line. Maybe it might look like this. It would have a different intercept and a different slope. Then if we took another sample, we might get a sample regression line that looks like this, a different intercept, a different slope. This number here is the estimated variance of the slope in repeated samples, and again we can take its square root to get the standard error, which is the standard deviation of that estimate. And so if we took repeated samples, this number here tells us that the standard deviation of the estimates we would get for B2 would be roughly 0.4. We'll talk more about that in week 4, but for now that is question 2 covered.